Hello everyone, welcome to another problem session. So today we are starting on this problem from Indian 2024 JEE Advanced Physics Paper 2. Now if you like the way I solve problems here from first principles, my approach is always to go to the first principles and identify the principle and try to implement it rather than kind of hand wavy way of doing things. Okay, so you can go this website can also help you. There's entire book on these kind of things. Okay, and concepts and problems. Okay, so what is this problem? I'll first saying that this as a first problem probably was not a good idea. This is a little bit hard problem and probably threw a lot of people off. There are a couple of, if you want to guess around and try to answer, you might say that you might have arguments. I say either this or this, and the one way to distinguish between them is where the EMF goes to zero is they are different, whether it goes at 3L over 2 or goes before 3L over 2. And you can't do distinguish between them without actually doing the problem. Okay, so we are let's look at what the problem is. Problem is that there is a ring and this is a conducting loop and is inside empty, it's conducting loop, and then there is a space. So this triangular is just a space and magnetic field is kind of pointing out in this area, and everywhere magnetic field is zero. So I say at t equal to 0, the ring is ring is falling at constant velocity, and you are bringing the ring down at constant velocity. You'll say if the ring fell under gravity and other conditions, okay, what will be the ring's speed as it's falling down? That'd be another question. But here is a really a little bit simpler question where ring is just, you're just bringing the ring down and it's going down, it's going down at constant velocity. So as a result, what will happen is inside this ring there will be induced current. Okay, so that probably you know as the ring is falling down. And then what is the law that actually guides this induced current? Well, that's the Faraday law, and the formula for that is in this PQR we're talking about in EMF induced in ring PQR will be E equals minus d phi b dt, right? So d phi b dt. So what is phi b? Phi b is minus, and phi b is integral, not minus, integral of b dot dA. So dA is the area of the loop. So dA is the area of the loop. So this is over area of loop PQR. Of course, over here right now there's nothing, so it's going to be 0. So as it's falling, there are two situations you have to really worry about. That's why there are two of these segments of induced EMF. One is when it has fallen but hasn't touched the tip, hasn't really hit gone through the bottom part of this triangle. Okay, so one situation is this. I've got to draw equilateral. Let me use the actual drawing tool to draw it. Okay, so I drew out the pictures so I can refer to it. So this is a situation at some time t where the tip is still inside this triangle where the magnetic field is non-zero. So this is the area that will contribute to it, right? So if you carry out this integral, you will have, and b is constant, and if you take this area to be vector pointed out at us, say, so this is along the z-axis, and this is also along z-axis. So that would just mean this area we're talking about positive current will be that way. So if the current is going this way, that will be negative current. Okay, so that's the positive current direction we're choosing, and so it's circulated that way. Then positive area will be in this way. So we have, this will be the B will come out, and just the dA where B is non-zero. So this thing just turns out to the B times the area of this, but non-zero, where B non-zero. So this area is area of this loop in which B is non-zero. So this is the area. So in this time, so that will be like in these figures, this will be the time before that. So this is the time we're talking about, this time, and all of them are the same. So it should turn out very simple to calculate. It is very simple to calculate actually. So this is x, and so if this kind of parallelogram kind of structure, so we can do many different ways. We can say, can we find this area of this triangle and double the area, right? So this is x. This is equal to this 60 degrees. So this is half of that, so 30 degrees. If I look at half of that triangle, this is x over 2, and this is 30 degrees. So we can find this as a base times tangent, right? So x over 2 tangent 30 degrees, and which is x over 2 1 over square root of 3. So this area is that way. So the area of this will be 2 times that. So area of this thing will be x over square root of 3. So area, I'm sorry, not area of that. So this is just this height. So let's look at the area of this guy. Area of this, you really don't need to just area of this guy. You can see I just figured out this distance is that much. So this distance is x over 2 square root of 3. So this, in this triangle, you have a base is x and height is that. So the area of this is half base times height. Base is half x, and x over 2 square root of 3. And the area of this whole thing, this area will be this area A will be 2 times A. So one of the half will go. So x square over 2 square root of 3. So before we work this out, let's carry this what the EMF we expect when it's falling before it has reached this depth. Okay, so let's So flux during this time, so this is when x is 0 less than equals to L case. In that case, flux is B times x square over 2 square root of 3, flux at time t, and x is a function of t. xt is given to be v times t, right? It's given over there. It's falling at a constant velocity. So that's going to be, okay, so minus d phi, this is magnetic flux, dt, it's just going to be b over square root of 3 to cancels out x dx dt, and dx dt is just v. So b v x over square root of 3. So it's going to be this minus here and minus here. So EMF is minus. So this is the slope, and this is linear. So it's all of this. So the slope is all of them the same. This gives you the slope is BV is negative BV over square root of 3. So that's the case for that. And actually that's not a distinguishing thing, though I did need to work it out, but it's good to work it out because it tells you that this is the one, this is the correct procedure to follow. Now when we do this part, this is the part when x, so this will be the case x is bit L, x goes to L and to L. So this will be the case for that. Now the area of this PQR loop, that where the magnetic field is non-zero, is the hexagonal area, and it has symmetry. So like this triangle here and this triangle here, so it's going to be 2 times this triangle, these triangles, and plus this area of this rectangle, and that's what we're going to work out. Okay, so bear with me. I'm going to erase this and clean up and then come back and try to do that part more cleanly. Okay, so it actually turns out to be the procedure we followed for this is also works out for this. So this triangle, if this is 30 degrees, then over there is also 30 degrees. And if this height here is 2L minus x, L minus that, so this height is 2L minus x. So so let's look at this triangle part here. Triangle part 2L minus x, and you have 30 degrees. Once again, I've got the same situation. So this will be this will be 2L minus x times over 2. So this triangle, we're looking at that triangle now. In that triangle, over 2 times tangent 30 degrees, which is 1 over square root of 3. So all of this will be the area of all of that will be half times this base times this height, 2L minus x, and height is this stuff, 2L minus x over 2 square root of 3. So that's the area of one of them. And then so we have another triangle, so and then rectangle. So what are the rectangle area? Let me take a pause here. Okay, so I drew it out. So over here can be used to figure out what the width of this rectangle is. The height is 12 minus x, so the width is can come from here using exactly same thing. It will be x minus L over square root of 3, and together the whole thing will be 2 times that. So the area of the rectangle will be 2 times x minus L over square root of 3 times 2L minus x, right? And so the area that we're talking about that has magnetic field non-zero is equal to 2 times area of the triangle plus area of the rectangle. So we can add these guys up. You have a 12, and this is, you can square it, 12 minus x square over 2 square root of 3. But this one doesn't get squared, 2 over square root of 3 x minus L 12 minus x. So this is the one. So when you get an EMF is going to be minus B dA dt, and so I have to differentiate the whole thing out, and let me pause and write that out to save time. Okay, so I went ahead and simplified it. So if you these are the same coming from these two terms. This one gives you this, and then the integration differentiation of this gives you that, and differentiation of that gives you that. And you can simplify this. Actually, you can see this is the same term. If I pull v of square root of 3, then a lot of things inside get simplified because they're all common. And you can say you have a 3x minus 4l, so we'll pull 3 out. So this is the case. So you can see that that E will go through 0 at x equal to 4 over 3l, not 3l over 2. So this must be wrong. So this means E is 0 when x equal to 4 over 3l. And it also says that the EMF will remain negative when x is less than 4/3 L, and it is negative for x less than 4/3 L, and then is positive for x greater than 4/3 L. So this is the EMF, right? So you can see it comes down and then it crosses a little bit before 3L. 4/3 L is actually less than 1.5 L, right? This is 1 1/3 and 1.5. So it crosses before that. So this is the correct answer. Now this was actually depends on your perspective. It's not hard problem or easy problem. It becomes hard because we rarely in physics we don't really practice this kind of shapes, and so when you look at the shape here, you might get a little daunted, like how I'm going to do the area under inside the loop. But otherwise, it's a pretty fair game. This question, difficult but fair. All right, so I will see you in the next video. Okay, take care. Bye.